Mhm.
All right, so I started recording, guys. Welcome everyone. So this week we're going over two other problems. One of them has three variations, so realistically we're going over like five problems. So I'm gonna start sharing my screen with everyone. Share, there we go. Hopefully Zoom is recording my screen too and not just our faces. All right, so I'm gonna start with problem 11.8. And I'm just going to go over the problem statement first. So it says,
Yeah.
many algorithms require as a subroutine the computation of the kth largest element of an array. The first largest element is simply the largest element. The nth largest element is the smallest element, where the n is the length of the array. So, for example, if the input array is basically 1, 2, 3, 4, 5, then a of 3 is the first largest element, which is obviously 5, and a of 0 is the third largest, which is 3, right? And then the fifth largest element is basically 1, which is a at the index 2. So the hint says use divide and conquer in conjunction with randomization. So I tried to use this hint to solve the problem, but I wasn't that lucky. And I realized that I was like wasting too much time on it. And then, this is what I usually do. I usually go and like read the first two lines of the solution, then I know what to do because that's what they usually explain. But as a result, I came up with a bunch of other solutions. So the naive solution is basically just looping over. Wait, where's the naive solution? Oh, it's a one-liner. Woohoo! All right, here we go. So the naive solution is just using Python sorted algorithm and then reverse it and then return the index like k minus 1.
Mm-hmm.
So I just wrote this in one line and then passed all the tests and I was like, nice. Now I can like work from here and just like make something that's better. So this has it's at best probably O of n log n. And then accessing that is linear. So accessing that is constant time. And then another solution that I came up with that is probably pretty cool, I think.
Wait, can you just go up to the naive one for 1 second?
Yeah.
So one
Let me see if I
thing
can,
I
like,
just wanted to point out one thing
yeah.
that you might want to know. So the sorted, there's two functions in Python. There's like sorted, and then you can do a dot sort on the actual list. So when you do sorted, you actually like created a new list there. So you actually use that much memory, and then you return that element.
Okay. But
So just FYI. So if you did, so if you did like non-sorted list dot sort,
Right.
then it would sort it in place for you.
Sorts in place.
So you're basically just using it for the side effect as opposed to actually returning something. So it's more like deviating away from like functional programming and going into like the side effects of imperative.
Yeah, I'm all functional, baby. No, thank you. That was a really good
Just
point.
a point, because I was like, because I remember when I remember when I did that solution, I even wrote a note, I think, in mine that I used sort versus sorted because I was like, what's the difference of these two? And then I realized that it does make sense that usually you'd have
I
one.
always assume that one exists in Python and the other one doesn't. And then I would do a Google search and the first one that would pop up, I would just use that because I would always assume that the other one doesn't exist. Because I don't know, different language, different thing. But cool, thank you. And
I think the way Python does
that'll be like such a big flex. Like, oh, by the way, I know how Python's internals work. All right.
I think in general, like the most languages will use like either like a present, was it like present tense? I don't know, something like that, or like sorting, like in ing, like it'll end like that if it's a side effect, and you're acting on that thing, and they'll use like the past for like I can't remember what they're called, but like sorted and versus sorting or sort. So that's like a hint for in general anything that's acting on an object instead of creating a new one.
Interesting. All right. So I have my other solution. It's basically I keep a stack, and this is a max stack, and then I will keep the basically highest n values that I find and I put it in that stack. So it's basically, let's say you wanted to just keep like calculate the maximum. What you would have to do, you could basically do it in linear time, right? You would have a max val, and then you would just iterate through your list. And then whenever you would find something that's bigger than that, you would replace your max value with that. And then that would be your maximum. So what I'm doing here is something similar, and except that instead of keeping the maximum value, I will keep the maximum K values as I go through the list. And then at the end, I will just return the first element in that array.
Wait, how do you update the list? How do you update the stack?
So basically, updating the stack is the part where it kind of could suffer from performance a little bit. And that is the stack is already sorted. So every time that you're putting something in it, you just have to like loop through it until you find where that item would belong, and then you would just insert it. So it's basically an insertion sort on the stack.
So there's no like, is there any reason for it being a stack versus just a general array?
And this is a general array. I'm naming it stack.
Yeah. Okay.
It really is general array. And then the complexity is is actually interesting because it's O of n k. So if k is small, this is actually linear. But if k is in the order of n, this becomes O of n squared.
Wait, it's O of n.
Time complexity, sorry.
Yeah. The time complexity is O of nk because you go over all n elements, and you go through k because the stack is of size k. That makes sense.
Yeah, exactly. You have to do a search of size k every time you insert something. And then space complexity is O of k. Space complexity. So it's a pretty good solution. I mean, it's different than what the book had. So something new to keep in mind. And then what else? And then we get to the book's solution.
There's so many solutions.
So there's basically my solution from book's idea. So it was pretty interesting. The book had the radix sort kind of idea to find the kth largest element, which was pretty cool. So you basically choose a random element, and then you set that as your pivot. And then you basically, you partition your array so that all the elements larger than the pivot are on the left and the smaller are on the right. Well, we've done the, what was this? That sort? It was called quick sort.
Quick sort.
Right? Yeah. So we've done like the Dutch partitioning flag problem previously. Yes. So I pretty much like banged out. It was pretty cool because I exactly knew it took no time to actually write this part, which was pretty cool. But I did it in 2 passes because the 2 passes is generally just like simpler to think of. And then, at least for me. So you basically partition this. So all the elements larger than that k are to the left, all the elements smaller are to the right. And then k will be that. So here, this I will be that element that I initially chose. So if I is exactly k minus 1, so we know that this is exactly the kth largest element. So we just return the value at the pivot point. So we just happen to choose it right at that time. And then if I is less than k minus 1, it means that this is basically not the kth largest element, but it's the basically ith largest element, which is less than k. So what we can do is to basically discard all the elements that are larger than this, and then look for the k minus I minus 1th largest element, and then pass the rest of the list back to the same algorithm. And then if I is larger than k minus 1, then we can basically ignore all the elements that are smaller than it, and then we can basically pass in the same list, but look for this kth largest element because we know that whatever we have, whatever our pivot was bigger than it was smaller than the kth largest element. So
randomness factor into this?
Sorry?
The randomness of it, how does it factor?
So the randomness pretty much just comes from the choosing the pivot point, and it reduces the probability that you would choose an element that is either the biggest or the smallest. And in that case, it would pretty much, reduce the increase the complexity of your algorithm, because every time that you're doing one of these, like worst case scenario, you would always choose the largest element or the smallest. Or smallest or the largest, really.
Well, it matters what k is.
Yeah. So like, let's say k is somewhere in the middle, and then worst case scenario, you always like choose something that's like largest or the smallest.
Yeah.
You would have to gradually just decrease your array, but every time it would only decrease by 1.
Mhm.
So it would be O of n squared, because every time that you do this partitioning, that's O of n. And then to go through the entire array to eventually get to your k, it will be another n. So it will be like O of n squared. The fact that you're choosing a random pivot every single time that you're going through this reduces the probability of that. So the complexity is actually with a, like, it's fairly confidently almost always linear.
Yeah.
In this case, which is pretty nice. And also the space complexity is pretty amazing too, because you pretty much have, actually, what is the space complexity of this? Is it just it's O of 1, right? Because whatever is
Yeah.
passed, you just like
Yeah.
reordering that.
Yep.
Cool. And then, so yeah, this is the only
I
part.
just wanna point out one or two things kind of. So
Yeah.
the first one was just about the complexity we were talking about. So the two worst cases, right, are when if k is like 1, so like the biggest element, then
Mhm.
that's the worst case if you just keep getting the smallest, because then you literally go through every element.
Yeah.
Or if k is the length of the array, then that means you want to get the smallest.
Yeah.
And if you keep picking the largest one, then you go through the whole array again.
Yeah.
That's for the time. But I actually wanted to point out for your two loops. So if you remember for the Dutch flag partition,
Mhm.
the goal of the Dutch flag partition was to partition it to 3 groups, right?
Yeah.
And then you did 2 loops, because the first loop would do everything greater than the pivot, or than some group, and then the second loop would move everything less than that pivot.
Yeah.
But if you notice in this question, all you needed to do was actually move all the elements that are greater than the
Mhm.
pivot to one side. So you actually don't need the second loop, because by definition, if you already moved all the elements greater than the pivot, all the elements before the pivot are already smaller than the pivot. So what you did is, like, in the second loop is already done for you in the first one.
Well, that's what I was gonna actually point out. There is one special case where you don't know, like, you want the pivot to, like, the you want all the graders to be left, and then you want your element, and then you want all the elements that are smaller to the right. Right?
Why?
You have 3 groups. You basically have all the elements that are greater, and then you want your element, and
Yes.
you want all the ones that are smaller to the right.
Sure. But
So in the case that you are actually like reordering all of these guys, it may be the case that your elements might be not exactly where the greater elements end.
because I just see what you did. Yeah. So the way I didn't realize. So yeah. That's a problem. And
Yeah.
the way that's
So
actually usually addressed,
yeah,
I don't know
here.
if you address it after.
I did it here. So I basically
Okay. Beautiful.
I read the book solution, and it's pretty cool.
Yeah.
What he does is basically he just replaces it with the end of the array, and then does the same thing, and then replaces it back where
Yeah.
the biggest ones end. So basically, you can just do it in one pass, which is really cool. I actually, oh yeah, here it is. So you pretty
Yeah.
much take the A of right and the pivot index that you chose in the beginning. You just flip them. You go through, you partition, and then you flip them again. And then you will get all the ones that are bigger to the left, then your element, and all the ones that are smaller to the right, which was really cool.
Yeah. That's very interesting, because I think I did the exact same thing, and then I saw the same thing in the book, and then I was like, wow, this is beautiful.
Oh, nice. Yeah, no, I didn't come up with that. I kind of just banged out the solution as soon as I read the 2 lines. But yeah, that's pretty much how this problem is solved. So kind of like 4 solutions. I mean, really 3. One is just has the addition that I.
Oh, and there's one more thing I wanted to point out, actually, when you go to the stack one. So it's really interesting to do the stack one, because it's like an actual missed step that the book didn't really mention before their like middle solution, which actually I think the stack one builds up nicely too. So you notice that your issue there was that searching for the largest element in the stack, right? That was like a pretty annoying thing that was k time.
Yeah.
So the beauty is that you can do everything you just did, but use a heap, because the heap will have log k search time
Yeah.
and log k insertion time. So you basically do the exact same thing, and it becomes the exact same like a space complexity, but the runtime is now n log k versus k. So like if you're using a stack like this and you need a min or a max element and you're searching through linearly, you can almost always use a heap, which is like a good point.
Yeah, exactly. I can just keep a min heap, and then I will take the minimum of it.
Yeah, exactly.
And I will basically pop the minimum of it whenever I need it. I would
And to add to that, I would say that your choice of whether to use a min heap or a max heap will be determined upon the length of the array that you're using. So if it's a short array, then you want to use a min heap. But if it's something that has like 500 elements, then you might want to use a max heap instead, because it's actually faster to go the other way. That's another thing that you can think about.
That's so interesting. So
Yeah.
like,
And
if your k is super, super large, or like bigger than half the size, then
Mhm.
you're,
Yeah,
you're
you do the other way.
basically looking for n minus kth smallest element instead of kth largest.
Yes.
right,
Yeah.
Damn, that was cool.
yeah, this touches on what we did last week. We talked about the use cases of min heaps versus max heaps, and
Yeah.
how it's not always, you're not always going to use a min heap or whatever when you're looking for a max, and the other way around. It's pretty much like something that you can add in the interview and say, okay, well, if we knew that the use case was on large arrays, then this is the kind of data structure that I would use versus another type. So it's like a little extra point on your scorecard.
That was really cool. Thank you. I learned many new things.
Imagine if we
Alright.
had this question on interview going through all the little points. that we
Yeah, I
mentioned.
know, right? You would have to
Rip.
mention you would have to mention that you've seen the problem before, otherwise it's going to be obvious.
Yeah.
But
Well, I
alright.
mean, most likely they'll give you some sort of, they won't give you this. They'll give you, instead of maybe the largest element, they'll find the smallest element or something that's a variation of it. So you actually have to think.
Yeah.
All right, Ziad, take it over from here.
Yes, sir. It's all you, man. Let's
Bar one. Okay, so this is, yeah.
8 Ziad bar 1. There we go.
All right, so, okay, I don't know why this is underlined like in red. It could be because it's some imitation part or something like that. Anyway, so a couple of things about this solution that I like. So disclosure here. So I kind of had like my own way of doing it.
Wait. Sorry. Let's go over the problem. Sorry.
Yes.
Yeah.
Oh yeah. Sorry.
So sorry. So yeah. Design an algorithm for finding the median of an array. So that's basically a variant of the previous problem that we solved. Okay.
Nice.
You can take over.
Yeah, it's a variant because it uses a similar approach. And the similar approach here is that we are interested in splitting the array into, using a pivot and looking for what's less and what's more, and then going from there. It's kind of the same algorithm or a very similar variation to what's in the book. Now, what I found here is a solution by Russell Cohen, who has a web page about it, and he's got an even better solution than this, which we'll go into in a couple of minutes. But let's go over the algorithm here. So we find the median using quick select, and quick select is basically what Arshan did and what the book did, and it's basically like a spin on quick sort. It's where I think the guy that developed quick sort and quick select is like the same guy. So here, let's go through find median with quick select. The first line here is checking if the array is of even or odd length, and based on that, we're going to choose the right path for executing our recursive function. So if the array is odd length, then we know that a single median exists in the middle of the array. However, if the array is even length, then we actually want to take the average of the two pseudo medians. I'm saying that like quote unquote. So they're not actually medians, but they're where the median should be. They are to the left and to the right of this missing median. So the first thing to note about the solution that I really very much like is the use of, if you guys look in the parameter list of pivot fn, so pivot function, we're passing in a function as a parameter to the function, and that's great because in Python, like in many other languages, functions are actually first-class citizens, which means we can pass them in just as we would with any other data type, like integers, arrays, and so on. And it's nice to be able to pass them in because it's an element of functional programming that makes that reduces the number of side effects really that can happen from execution. So going through this, let's go over the quick select function, because we can see that we're pretty much doing the bulk of the work with the quick select recursive function. So here, yeah, I think it's an indentation problem. It's because I used another IDE to do it, and
Yeah,
then
probably.
I could copy paste it in here.
Sorry.
So
I'm just cleaning up a little bit. Okay.
yeah,
There you go.
and so yeah, true. Yeah, so from here, the first step is to check the length of the non-sorted list, and if it's 1, then we know that the median is the only element in the array. Otherwise, we select the pivot, and the pivot we select is using the pivot function on the non-sorted list. And this is nice because the random choice that we're choosing will depend on the length of the non-sorted list. So if the non-sorted list is only an element long or 2 elements long, obviously you don't want to choose a random number like 3 or 7 or 17, right?
Mm-hmm.
So this has the benefit of scaling with the length of the non-sorted list. I'll use something really neat here. I think this is called, what did you call it last time? List comprehension?
Mm-hmm.
Yeah, list comprehension.
Is that from Python, right? So that's really nice. We split the array, the non-sorted list, into a bunch of like an array of lows and then highs and then pivots.
Mm-hmm.
And then based on whether the item is less than the pivot or greater than or equal to. And then
What's the point of splitting it into these lists?
Because then we perform, so then we're gonna, so this is the interesting part. So in this algorithm, we can see that K is gonna be the, K's largest element or whatever. So it tells us by itself that the number itself, the K is an indication of, or rather is related to the length of the list that the lows and the highs will have.
Yeah.
So if K is a large number, then there will be the length of lows that we create will be very large, or very small rather.
Right? Let me just, so is the list just used so that we can get its length to compare to K after?
Yeah, pretty much. And then we also use it because when we recurse, we're going to use it, we're going to recurse over that.
Oh, we pass it in.
Yeah.
We pass it in.
Yeah,
just one thing is, I think this is pretty much like we could have done, like this is exactly like quicksort, except that it's not in place.
Yeah.
I think. Like what you're doing here is exactly like what we were doing, kind of.
Yeah.
But like
if you concatenate these, you
nice,
will get the same kind of partition.
Yeah. So I mean, it doesn't have like too much novelty to it. What I do like is that it's pretty clean.
It is, yeah.
That's partly because it's because of Python's ability, or like the way that Python was kind of created, and the fact that we can use list comprehension, and we can also use functions and pass them in as parameters. I really like this solution. And then from there, we return. We eventually get to the base case, which is that we found the pivots of 0 is going to be the pivots at 0. So the first element of pivots is going to be the item that we want to return. Now, a big thing to note here is that we can improve this algorithm further.
Wait, so I'm still a little confused. How do we narrow it down to the median?
So we narrow down to the median because every time if you look at the if, else if statements here, based on the value of K in relation to the length of either the lows or the lows plus the pivots, we're going to recurse with different arrays. So let's say we get to the point where we hit the first statement, K is less than the length of the lows. Then we're going to recurse quick select, but this time instead of using the non-sorted list, we're going to use the subset of it, which is just lows. We'd be using K and the same pivot. So the second time that we go over it, we'll find another pivot that's going to be scaled down to the list, which is just going to be the lows. And then we keep re-executing the same kind of logic until we hit the case where K is going to be the median that we're looking for. So we're
But
making the problem
how do you
smaller.
set K? Where do you set K? I'm just confused by that.
I think he sets it up here. So you basically,
Oh.
K is
Oh, we're looking at
length
that function.
over 2. It's K
Oh
Oh.
is
yeah,
length over
we're
2.
looking at this function, not the one above it. Yeah.
Yeah, so in case that it is,
I didn't realize we were using the top function. I understand now.
yeah, it's like,
Oh, I see. Yeah, so what we're doing is we're basically doing the quick sort or the quick select thing, which is what Arshan did more or less.
yeah,
And then you just pass in 2 cases, which is if it's odd, then you pass in the middle one, and then the other one you take the average or something like that, right?
That's right.
Yeah, you take the
That's
average.
right.
Oh, okay, this makes sense now.
that's pretty cool. Yeah, actually,
Now,
yeah, okay, go
yeah,
ahead. Sorry.
there is something that I do want to point out. It's this is technically not the best solution. The best solution makes use of a better choice for the pivot instead of random.choice, which is using the concept of median of medians. Now, it's just a longer and more elegant way to find our pivot. So we no longer use random. We use a pivot that we know is not going to be the largest or the smallest element, whatever the case may be, of the function, which guarantees, from what I understand, that you will never hit that O of n squared worst case scenario. So it'll always be O of n.
How do we know?
So
How do we find that pivot?
Yeah, how do we know?
The median of medians, like the pivot. So I didn't understand it too well, but if you click on the link,
Yeah,
towards
let's
the
go
bottom
here.
of the page, scroll like 3/4 or something of the way to the bottom,
Okay.
or like a little up. Go up a little bit, up. Yeah. So right here, this is how he finds the median of medians. So if the actual function starts at the top of the block of code.
Quick select median.
Okay. So
Pick
yeah,
pivot.
pick pivot. So pick a good pivot within L, a list of numbers. This runs if O and O of n time. So it basically goes through the thing and then makes sure that it picks a pivot that is like half biggest.
Mm-hmm.
Yeah, that's what it seems like.
Looks like, yeah.
Which is an O of n time, which is interesting that you.
But wait, if picking your pivot is O of n time.
Yeah, that's what I'm interested in too.
And then you're running the pivot function n times yourself. Actually, no, because if you pick your pivot to be half, then you only have to run it once. After you partition, you will land exactly on the median.
Yeah, but we're solving that problem.
But that's, yeah, like how
Pick the pivot as half, you have to solve the problem we're doing, which is probably not what he's doing.
Yeah, this is curious.
Yeah, I'm probably gonna look at this after. Yeah, I don't think we should look at it now, but it's interesting.
Yeah,
to
it's a really good post. It's this guy's favorite algorithm.
Okay, cool. I like this. Let's take a look into this and just like bring it up next time.
And I suggest that for future problems, if we find something neat, we should totally link the articles or posts or whatever, because those are usually the cases where like it deviates from the solutions that you find in books and stuff.
Yeah, okay, like EOP, I know.
It's real nice.
Look here. Boom. Okay. All right, cool. Thank you.
And that's it
cool.
for
what I really like is this pivot function, because you can like pass it in.
It's beautiful because of that. Yeah, because it's functional programming, and it's very clean, and it's something that almost always, if I can, I try to choose functional programming over side effect prone code.
It's interesting though. I mean, like it really is sometimes a matter of kind of like taste too.
Yeah.
For example, at my last co-op, my manager was writing almost all of our code in like pretty much very much object oriented. But then he started like playing all these functional programming videos for us, but no one changed. No one switched from what they were previously doing. It was just a matter of just like us knowing what the other paradigm is like. And
well, because it's something that you're kind of it's something at the beginning when you're first learning, like, or when you're first starting to use it. It's something that you really have to force yourself to use,
Yeah.
because they're like, why am I taking this road when I can just take the shortcut? And the idea is that you take the high road, quote unquote, so that eventually when you get to the point where you find there's this weird bug that's crashing your whatever app or whatever you're doing, and you can't find it, it's because of a weird side effect that's happening. And this side effect could be from any of your function, because anytime you're not using functional programming, you're changing the state of the program. It could be something completely small, right? And trivial, but sometimes it'll be not trivial and it'll change your program in ways that you're not even supposed to just think through, right? Because it's like something completely unrelated to it. But with functional programming, we don't do that, because every time we're using the stack in the function, which gets recollected, that's the state that we're using. We're not using the actual state of the program.
Yeah, so
it's
that's
not affecting the heap. Everything is done.
Yeah, so I'm with different applications, this has kind of like different paradigms, work with different applications. But so in many cases, you might actually have to have a state for example, if you're making like a form in a website and you want to show something based on like some variable's value, that is the state of your program. So in functional programming, what you do is that you keep that value on your stack. But you are basically, still using the same variable. But I guess one thing that functional programming does do is that it makes these state changes more